So today we're going to talk about vibe coding at scale, how we discovered about 35,000 vulnerabilities exposed on AI-generated web applications, and how did we automate and scale this at a large scale on the internet. But first, let me introduce ourselves. I'm Nohé. I'm a research and development software engineer at Escape. I'm the lead of the attack surface management, and basically my job is to automate discovery and pen testing at scale. I'm a former NSET and TLSEC student.
And hey everyone, I'm Gabin. I'm a security research product owner, and I'm in charge of the result quality in the Escape platform. And I'm also an NSET and TLSEC former.
So this talk is based on research we've done. Basically at Escape every year we publish a security report. This one is the state of security of vibe-coded apps. You can read the full report and methodology there. We won't have time to cover everything, but basically it's that, and I'll present you that. But little introduction, how did we get to vibe coding? Probably now everybody in the room has at least heard the term. Basically it all started in 2023 with the rise of LLMs being adopted to write code. But at first it was with tools like ChatGPT. You just went on chatgpt.com, prompted something, it would give you the code, you copy paste it, you put it inside of your IDE, and then you run it manually and you edit it and you iterate like that. Then, based on that, we've seen the emergence of tools like GitHub Copilot or Cursor, Cloud Code, etc., that were integrated in the development cycle, and where the goal is to have them, the agents or the LLMs, directly code with you in the IDE. And from that emerged the term vibe coding, which has kind of a hype or like a term that emerged, which was using these platforms, but in a way where you let the LLMs do most of the work and iterate themselves, and you try not to look at the code, or you just let them automatically generate code. Based on that, a few platforms and companies started, such as Base44, Lovable, but a ton of others, where they built tools that allow you to create applications, web applications, directly from a ChatGPT-like interface, like a chat. You just chat with them, you have a preview, and it generates the code, it generates the front end, the back end, it deploys it for you, and it does everything, and it basically allows to build application with just text-based editors. Little question to the audience by raising hands. How many of you do use LLMs or AI in your job, day-to-day job, or studies? Yeah, that's what I thought. It's like almost everybody. Is it to write code? Yeah, a lot of people too. Basically, I've been asking this question for a few years almost now, and the adoption have just been raising, and probably now it's not even, there's not even a point to ask it anymore. It's like global adoption. So at Escape, we also do use LLMs to help us in our job and to build tools, but we've all experienced, and probably you have too, that LLMs, they produce bugs, they hallucinate, and they can create weird results if you do not harness them correctly and if you do not review the code. And this is even the case when you supervise it by a competent human, like you're an actual software engineer trying to use an LLM. So probably fully AI-generated code might be worse. Also, these platforms, they necessarily lead to unreviewed code because they just give you a text interface and it's completely obscure, and if you want the access to the code, you need a couple of steps to do it, and it's not meant to be reviewed. Also, these platforms, the whole point is to create code by less technical people. The goal is so that non-technical people can build apps, and so we thought that might be a problem. And the last point is, as I mentioned, at first these platforms were designed to do UI job or like front-end development, which generally speaking has less impactful vulnerabilities, but now they generate also your backend, your database schema, the infrastructure to host it, and so they handle the sensitive data in the database. And we thought there might be some nasty security issues there, and that's what we wanted to prove. On top of these assumptions, we have a few catalysts. The first one is that we've seen a clear increase in attack surface in organizations. This is based on our 2025 report. We've seen that on average, organizations now have 15,000 endpoints exposed on the internet, and we've seen as much as 3,000 single different API services exposed for a single organization. And this is like a global shift, and AI is accelerating that. The second catalyst is that on top of the increase of the number of the attack surface, there is a clear increase in attack as well. This is a report by Kong, and they forecasted that by the end of the decade, we will see a 1,000% increase in API attacks. So if we get all of that, we get kind of an explosive cocktail. The companies, they have more application that they can track, there is an increase in reported attacks, and there is no more human in the loop. So we wonder what could go wrong. So to prove our point, we needed a methodology. And the first thing we needed to start with was an input. Where did we start? The first source we started with was Lovable Launched. It's a leaderboard where when you build a Lovable application, it ends up on this leaderboard and people can vote for the applications. So we could just scrape that, extract the applications, and start with that. On top of that, we also discovered that most of these platforms, they inject either JavaScript tags, comments, or CDNs, specific CDNs that they might use. So we took these fingerprints, we have a couple more, and we ran them through Showdowns or similar internet scanning tools to identify a lot of applications online. We also did some subdomain enumeration and discovery techniques on the subdomains where they deploy the apps by default, like lovable.app, base44.app, etc. And we did some OSINT and some manual searching. After filtering, we ended up with about 5,000 base targets for our study, and we were ready to start with our tooling. So once we have these 5,000 applications, how did we do? We input them into the Escape platform, which is an automated security platform for the first phase of reconnaissance. Basically, the reconnaissance will take these assets, which are web applications, and we'll run some scanners on them to find more assets or increase the context on the assets, like find metadata, more on that later, some context about them, and try to find some surface vulnerabilities and some risks about which application might have which risks at which point. The recon functions like this. Basically, we input assets, which can be of very diverse types, a host, an API service, a web application, but also a lot of different types, but which were not necessarily used for this research. Then we run them through composable scanners, and we create a feedback loop because these scanners, they output new assets and vulnerabilities, and we will rescan these assets so that we have a recursive scanning, which allows us to map a very large attack surface over time. Basically, one of these scanners, they are all kind of built the same. They start with an asset. They try to do validation or reachability, like can we actually ping the asset? We try different proxies in different locations in the world. Then if we can, we do some fingerprinting and we search for metadata on it. Is it using a web application firewall? Is it using some cloud provider? Which framework or library is it using? The GeoIP, some information we can collect. Once we've enriched the assets, we push it in parallel into the discovery phase and the surface scanning. The discovery, its goal is to find more assets. So basically, we will like parse the base thing is like subdomain enumeration, parsing responses for URLs so that we can find new assets in our scope. And the surface scanning, the whole point is to find vulnerabilities. And sometimes we also do find assets from that. Let's deep dive a bit into the surface scanning for web applications. This is a simplified view of basically how it works. Basically what we do is we take the application, we start a web browser which we automate with code, and we crawl the application. The goal is to understand how the application works, which fields are available to pen test and to inject, and once we've explored and we understand the application, we can run some active injections and security checks. While we are doing that, we also hook into the browser so we can extract every network call and every JS source and other sources that the application might be using. And on these extracted assets, we will run some passive security checks, some secret or personal information detection, and try to extract more assets, like we can reconstruct the schema of the API the web application is using because we see the network calls. We can extract the auth, like the cookies, the tokens. We can extract a lot of stuff. And then we will build context and keep that, raise some issues if we are able to find them, and reuse them later on. One thing we quickly realized while doing that and reviewing the first iterations of the results was that Lovable, by default, and other platforms, they do not actually code your backend. What they do is that they use a service called Supabase, maybe you've heard of it. It's basically a hosted Postgres database, which also sets up for you a REST API that serves your database as an API. And what I thought was really weird and probably really insecure is that how Supabase works to expose your API is that they use something called row-level security, RLS, That's kind of rules to map authorizations and different roles to access control in the database. So like this role this token has this role, and this role has access to a specific table or specific rows in specific tables. And this is easy to miss and to misconfigure. Even as a human, when you're experienced, it's super easy to misconfigure it and to get it wrong. And so Lovable is configuring it directly via the API via LLMs and agents, which makes it probably very insecure. So we focused on that a lot later on. And also there has been a CV reported that Lovable was misconfiguring it by default, and we are able to reconfirm it later. So we ran this discovery for a couple of days, and we started with 5,000 base targets. We ended up with about 15,000 discovered assets online, and out of which we had 6,000 web applications, about 1.5 we kept. I will explain the filtering, and about 1,000 API services, and we kept about 500. So why did we filter, and how did we filter that? That's my last point on the recon. Basically, the vibe-coded applications were really broken. Who would have guessed? A lot of them were just like web pages where you click on a button, the web page crashes. You cannot use the web app. So we filtered that, and we removed it. Also, we removed the fully authenticated web applications where a public user cannot perform actions. And we removed the landing pages or static websites because it's way less interesting from a security standpoint. On the API side, it's kind of the same, and we focused on the Supabase APIs. So now that we have these filtered, context-enriched, and discovered applications with already surfaced vulnerabilities, how are we going to escalate it to find real critical vulnerabilities? I let the floor to Gabin.
Thanks, Nohé. So, at the time we wrote the paper, we were also developing one new product at Escape, which is called the AI pen testing. And we decided to use it for several reasons in this paper. The first one is because it was helpful to help us to benchmark what we were doing and see if we are going in the right direction. The second is because the AI pen testing inputs can be very flexible. So we are able to input tested applications as assets, and we are also able to input all the ASM potential vulnerabilities and a lot of what we are calling artifacts as API schemas, sitemaps, JS bundles. So we are able to input applications, but also lots of metadata around that in our AI pen testing tool. The last reason why we are using the AI pen testing is because it's very helpful to help us detect complex business flows. I have an example for you where, for example, you have an endpoint with some user PIIs that are available on the internet without any authentication, as for example, /user/user ID, where you can retrieve a name, age, and an email. Depending on the context, for example, in a bank, this is a very sensitive information for them, so it will be an issue. But for example, in a social media, this can be some information that is just a feature. So in legacy automated tools, to find that the difference between in the context of the application, it's required a lot of configuration. And with AI pen testing, you don't have this configuration to put. It's like basically the same as a manual pen test. At that point, you may ask yourself, are you really testing LLMs with LLMs? Didn't you say that LLMs cannot be trusted? They are creating security flaws. And the short answer is yes, we cannot fully trust them. But on another hand, we also can decide to automate it and to orchestrate it well and validate all the findings to be able to have way better results. Let's deep dive a bit in the AI pen testing configuration to understand how we are validating all the findings. The first phase is the recon. In the recon, we will try with an agentic crawler to crawl all the applications, to discover all endpoints, and to build a crawling map. With this crawling map, we will also report some hints. Hints are what is the goal of the application. We will not test an application that is a bank or a social media the same way. So we can build some different scenarios depending on the context. The second phase is the exploitation. During the exploitation, the orchestrator is the brain of the AI pen testing. At that point, it can decide to spawn specific agents, to crawl a part of the application, to test another part of the application, to decide to authenticate using one user or another. And every sub-agent can use tools, meaning they can use a browser, we can provide them, that can execute some Python, they can execute some Bash, and that they can share a memory between them to be able to share useful information between them. Every time one of the sub-agents is finding an issue, it's reporting it to the orchestrator, and the orchestrator can spawn a very specific agent. This very specific agent is a reporter, and it's going into the validation loop. Let's deep dive a bit in the validation loop. The validation loop, the reporter had a potential vulnerability, and depending on the kind of vulnerability, we will either use the canary validation or an adversarial validation. The canary validation is basically where, for example, in XSS, we are able to tell to the agent, when you want to report an XSS, please spawn an alert on the browser. And we are able to deterministically determine if they were able to pop an alert. And for other kind of vulnerabilities, where we can't do this kind of validation, we will spawn what we are calling an adversarial validation. This adversarial is another agent, but its goal is to validate two distinct points. The first one is the vulnerability makes sense. So is it useful in this context? Is it just hallucinations of the agent? And the second one is, am I able to reproduce the vulnerability? So the validation agent has pretty much the same tools as all the sub-agents. So it can spawn a browser, use scripts to automatize, and try to reproduce it. Let's now talk a bit about the results we had. But first, I have some disclaimers. The first one is as Nohé mentioned, we were testing only a scope of the applications we discovered, because a lot of them are broken or untestable for us. The second point is we weren't using any authentication. Why? Because at the time we wrote this paper in September, the AI pen testing was not able to support any authentication. So everything we did was with public users. And the last point is we were running all these scans in production mode scanning. This means these scans are harmless. So we disabled a lot of checks, including hard injections, and all the things that can alter the state of the applications. For example, on some websites, we were able to comment using a public user, but we were never trying to do that. So we can miss, for example, in XSS in this field, because we were not trying that. So all these kind of things can introduce a strong bias in our results. So we know we decreased our results and the severity of them. So let's go to results. We find on these applications more than 34,000 vulnerabilities, including around 100 with a critical impact and more than 2,000 with a high impact. All the vulnerabilities you can see in red and yellow, it's vulnerability we were able to validate by hand also. We also discovered more than 400 of secret leaks and 175 instances of PII leaks. In the critical ones, we discovered 4 SSRFs, 2 zero-click account takeover, more than 250 vulnerable dependencies. We reconfirmed 2 times the vulnerability on the RLS Nohé mentioned, and we find also some BOLAs, some file disclosure, including Git leaks, and some broken access control. When we saw these results, we were quite surprised on our end, because we are used to do things like this, and one of the things we were thinking is we are seeing way less old vulnerabilities than before, and an increase in some kind of vulnerabilities as business logic vulnerabilities. But in fact, it makes sense, because vibe-coded applications, or as low-level, for example, are made using Next.js. And this is very hard to inject to include XSS or SQL or common injection inside these applications. So you have a decline with this kind of vulnerabilities. But as, for example, the RLS is very difficult to configure, you have an increase in BOLA, IDOR, and complex business logic. And now I will let Nohé present some results in detail.
Well, thank you, Gabin. Let's deep dive into critical vulnerabilities we did find using this approach, which I think are really interesting. The first one is a medical platform, which was leaking all PII and passwords of the doctors on the platform. Think of the platform as kind of a Doctolib alternative, smaller scale, but with actual people using it. You can see it was leaking the full name, the birth date, the phone number, the license number, which is like the medical license number, the bank IBAN, the email, the password, which is in clear, and the specialty of the doctor. It's probably as hard as you can get on dumping user info. Having the clear password is, you can escalate a lot of things with that, and you can probably do lateral movements to access sensitive medical content, and also try to brute force the password on other websites. So this is very critical. And the cause of that, the root cause, was the RLS I was mentioning. Basically, the application was using the API routes which were actually secure, like the proper payloads, they were secure, returned the correct information, and were not leaking the wrong information. But tweaking this payload and modifying the request a bit when you know how Supervise works, it was able to bypass some of this row-level security, and some part of it was misconfigured, and we were able to dump a table. The second one is a zero-click account takeover, which allowed to take over about 950 active sessions at the time of doing this exploit. So you can see it leaks the session token. So basically you can just copy-paste the session token in your browser and impersonate any user of the platform. And this is like all the sessions for the past few days, there is a bit of a cache. And the cause here was a broken custom authentication and combined with Ebola. Basically, the authentication was completely recoded by the agents. They used not a standard authentication and authorization flow. The agent probably hallucinated and thought, okay, I will re-implement a complete flow of authorization which had holes. And then with these holes, we were able to access disable, and with Ebola, access fields where we should not have been given access. So this is also a very, very hard vulnerabilities. Basically, if you log in a website, someone is just able to steal your account. And this included the full table, so you have admin accounts too. So, in conclusion, the question I wanted to ask, and this is kind of where this talk is going and what we are witnessing in the industry, is can AI cure AI? This is the question everybody is kind of witnessing within the cybersecurity industry. And I think at Escape we have a vision and we have 3 takes I wanted to share with you. The first one is that AI is here and it will stay whether you like it or not. I think like a year ago or even a few months ago, we could still argue that probably it was just like it will not be globally adopted, big companies won't use AI, it's just for tinkering or prototypes, but I think now it's been proven wrong. We've seen recently a leak that Apple is using Cloud Code to ship real applications because they leaked Cloud.md in the source maps. So it's being globally adopted and it will stay. The second take is, as we've seen, it's increasing attack surface at an exponential rate. Code is getting cheaper and cheaper to write every day, and it's just easier to deploy applications. So we are seeing a clear increase in attack surface and in entry points in organizations, and at the same time, these entry points are probably less secure than they used to be because humans are less and less in the loop. But the third take, which is kind of our point with this presentation, and is that it also makes security more scalable than ever. We are able to find vulnerabilities where traditional tools completely failed, like with a normal DAST, you cannot find very complex business logic flows, some complex bypass of payment systems, because it's depending too much on the application context and on the very specific implementation. So, and also we think that we can use AI at every step of the development and cybersecurity steps in a company to help you reduce the vulnerabilities. You can use it when you develop it. You can ask the agent to help you make it more secure, and then you can review. You can use it at the review step to kind of make sure you review everything, because it's becoming a challenge too now that we see more and more and more PRs. And you can also do some AI pen testing at the end to find more vulnerabilities and patch them and do iterations to reduce the vulnerabilities. But if we are able to do that, us and other companies and other people, so hackers can. And the same tools are in their hands. They are building systems to automatically find 0 days and vulnerabilities online. As we've seen recently, there have been a lot of CVEs which were found using AI. Two examples are the GitHub Enterprise CVE by Wiz, which is a very crazy exploit. I invite you to check it. And the copy-fail Linux kernel vulnerability, which is a privileged escalation, which got a high CVE and which was done almost entirely with AI. So we kind of have to defend with LLMs. If we want to scale, if we want to be able to react as fast, we kind of are obliged to use LLMs. So it kind of creates a race between who will win the race of finding vulnerabilities, whether it's like organizations trying to defend and to report stuff, or just people trying to hack stuff, not for a good purpose. And I'm also wondering, will we see major AI breaches in the near future? I'm pretty sure that yes, probably, and it's starting to arrive. And I wanted to finish with kind of a funny thing about our job. We realized recently that at Escape our job is to write AIs with AIs, to find vulnerabilities in AI-generated apps so that other AIs won't pirate it. And I think that's quite ironic, and let's see how it goes and where this leads. Thank you. I hope you enjoyed this talk. If you have any questions, we'll be happy to answer to you and to discuss after the talk. Thank you.
Thank you. Yes, thank you for the talk. So, as expected, vibe-coded applications are the worst, but do you think it can get any better, or is it meant to collapse? I mean, vibe-coded applications are based on LLM, LLM are based on learned from a code base, and soon this code base will be vibe-coded. So it can only collapse, or do you have any other reason to think it will get any better?
Yeah, I think it's a great question, and I think it's a major challenge for AI labs currently, because of course the number of applications and like code on GitHub is exploding with AI-generated code, which will like feed itself. But I think recent improvements in the models prove that kind of wrong. I think I'm not an expert in training LLMs, but I think there are solutions, and I think also now the harness, like what you do around the models to make them do what you want and to have guideline like we presented here is really important, and is where companies that use these models are converging, and we are seeing a lot of good practices to make the LLMs actually do what you want without this enshittification of the internet being in the loop.
Thanks for the talk. So I have a question. Do you think the vulnerabilities that are in AI vibe-coded application, the classes of vulnerabilities, are significantly different from applications that were coded by humans using the same frameworks? So like a human develop an app, is this the same classes of vulnerability or stuff specific to AI maybe?
Yeah, that's a great question. I think if humans, like if you start at the same date on like same technologies, you will indeed see the same classes of vulnerabilities, probably at a different magnitude. Like usually what we've seen is that when you use AI a lot, you have secure isolated bits, but as a whole, as a system, you often have like flaws in the bigger patterns, because it's hard for the machine to understand like large code bases, and especially in large applications, we see it ourselves. We have a very large code base, and it has a lot of pain to intricate the systems themselves, and so you see a lot more like broken logic and broken authorization and stuff like that, I think, but you still see the same vulnerabilities, just probably a bit less in traditional applications, and that's what we see on our customers, which we scan with this product.
Okay, thanks.
Thank you.
Thanks for the talk. Quick question. You claim you claim that, as a conclusion that that vibe coding is the worst. But have you compared with web apps that were not vibe coded? It's an obvious question, but without this, you cannot claim anything, right?
Yeah, that's a great question. That's kind of what this slide is about. When we did this comparison based on our previous research, which was kind of the same methodology, like scanning stuff at scale, but on different targets. The last one was like Fortune 500. So it was like really enterprise grade applications, and we really did see a very different class of vulnerabilities and different frequencies in the type of vulnerabilities we observed. This kind of large-scale enterprises had a lot of traditional old vulnerabilities like injection and stuff, because they still use like PHP, old versions, stuff like that, whereas the vibe-coded one do not. But of course, in terms of frequency, what we observe by comparing to our customers, for instance, is that on the vibe-coded applications, we had a higher success rate in finding vulnerabilities because probably they are just less secure by default.
Okay, do you have a source of the data set that
yes.
you compared? Or?
I think there is some comparison in the source here that I had at the beginning here. We have comparisons here probably, and we also have where I say that it's our State of API Security 2025, which was the research report before this one. So you can compare
only
it.
About API, okay.
Yeah.
Thank you.
Okay, thank you. We have to switch now to the presentation, next presentation. So thank you. Okay.